Thank you, Julian, for the introduction. Thank you for the opportunity to speak here today. And before I even begin talking about the science behind this study, I would like to thank everyone involved in this study. This study was supervised by Professor Juarez, and we have some collaborators. We have Stella Justo, that has a master's dissertation on this topic, and we have Jonathan Marinalva and Marcus, which helped us with the statistical analysis. They are from machine learning team. And we have Chris, Mauricio, and Mauricio also helping with the quantum chemistry side of things. And it's thanks to all of them that we are today here creating the stability and properties of 55-atom bimetallic platinum-based nanoalloys to understand the formation of core shell systems. But why? Why do we want to study these core shell nanoalloys? We want to understand the nature of these systems. And why? Well, here I have a word cloud. What comes to mind when I think about platinum-based nanoalloys? I think about a lot of things. One of them is the synergy that exists when you mix metals together. Metals, transition metals, they are well known for their properties, for their good properties for several applications. And one of the main ones that is inside the interests of our center is catalysis, that I put here in the center. Their optical, structural, magnetic properties can all synergize and optimize processes. One of them, one of the most interesting, is the dry reforming of methane through CO2. Well, but which aspect of the nanoalloys are we exactly interested in? We want to know about the core shell systems, right? There are several possible ways in which the two metal atoms can combine. The arrangements can either be segregated, like these ones that I show. The core shell type that I put in evidence here is one of the segregated types. And it can be a mixed arrangement too, okay? So there are various ways in which they can mix. And we want to know which nanoalloys of platinum combined with other transition metals, which of them will form stable core shell nanoalloys? Which ones? Which metal will combine with platinum to form these kinds of structures? And why? What are the factors that affect that drive the formation of core shell structures? For this, we have a model. We have a model that is the icosahedron, a simple icosahedron. It's a model that has one central atom that you see in gray here, and this single central atom is surrounded by 12 core atoms, so they make up for 13 core atoms, and there's an outer shell with 42 metals. So we have 13, 42. And we have a strategy to study these systems, to use quantum chemistry to study these systems. We come from a history in our group where a study of the unary system was made before. So the unary 55-atom nanoclusters for elements from the groups of iron to the group of copper. And they have more elements, but these ones are the ones that we selected because they're interesting for catalysis. And each one of them was studied in great detail. They applied corrections, they applied several types of structures, morphologies for each one of them. And what you're seeing here are the lowest energy configurations. So we selected these, for each metal, the lowest energy configuration, and we go here to our method to obtain the atomic configurations. So we have a unary system as a frame. We have the putative global minimum configuration, and we also have the icosahedron. That's our model. And in each one of these structures, we substitute atoms. If I start with platinum, I substitute platinum atoms to the other transition metal, and the other way also works. And from this, I generate the nanoalloys and optimize them. Okay, so we also worked with two compositions, with 13 platinum atoms and 42 platinum atoms. this is because of the model that has 13 and 42 atoms in the core and surface regions, respectively, that I showed before. And we employ density functional theory with the PBE approximation for the exchange correlation energy with the VASP software. Here, I show a summary of our results. These are relative energies. Above, you can see the platinum 13 composition, and below you can see the platinum 42 composition. If I explained well the procedure, you will understand that I have various possible morphologies and configurations for each one of these nanoalloys. And here I only show a summary. I show the lowest energy configuration, it's the 0 for each composition. And for each composition, I also have the highest energy configuration and one in the middle. Okay, so among them, I have our core shell systems. We want to understand why these results are what they are. So the first thing was to validate our method. Does it work? We can do calculations, but we have to know if what we are treating is relevant, if it's physically relevant, physically correct. So I'm showing here on the left the binding energy, and this behavior is it's a very well-behaved result. It's a known trend from the transition metals. Even the crystals have this behavior that is related to the D-band model. If you think about the atoms and the orbitals, the d orbitals interacting with each other, you will see a trend of the binding energy. If you come from the beginning of the periodic table and go forward, the binding will increase. The binding energy will increase because you are feeling ligand orbitals, bonding orbitals. And then you come to manganese, that's in the middle of the table and has a D5 configuration. And moving forward, that is from the groups of iron onwards, that's our results. You have the feeling of anti-bonding orbitals. That's an approximation, it's just an idea, model. But the model works, and you will see a decrease in the binding energy. The binding will be weaker. This will be reflected in the structural properties. The atoms will be further apart from each other. And this is what happens in our model, in our systems, for the pure nanoalloy, for the pure clusters. And for the nanoalloys, you have intermediate values to the values of the components. So we also measure the excess energy. The excess energy, oh, sorry, I forgot, but the binding energy is a comparison of the energy of the nanoalloy with respect to the free atoms. It's all about atomization. But the excess energy is about comparing the nanoalloy with each respective unary cluster. Those clusters, those unary clusters that were the most stable unary clusters can be compared energetically with the nanoalloys, and this is what the excess energy shows. So if it's below 0, the nanoalloy is stable, according to this equation here. And all of our lowest energy nanoalloys are stable, as the graph shows here. They are the bigger symbols, the larger ones. So to understand the behavior, the formation of core shell systems, we used some correlations with the excess energy. What you see here, the colors, they represent the correlation coefficient, the Spearman correlation coefficient. And the ones above here are one of the main correlations that we observed. We saw here that the type of atom on the surface is more important for stability than the total number of atoms in the surface. So it doesn't really matter, because this first correlation here, the first line, you have each column is a system, okay? And the horizontal axis for each square here is the excess energy. And the colors indicate how they correlate. And the first property here, the number of surface atoms, doesn't show really a strong correlation. But if you identify the atoms, the identity of the atoms, the type of metal, then you see strong correlations. and you'll see that they are different depending on the system that you have. There were many other correlations that we studied. One of them, the magnetic moments per region for surface and core atoms, only correlated well for the nanoalloys that have a high total magnetic moment. That's expected. For example, the 3D metals here with platinum. So there was these correlations, they will be used later to identify one of the factors, one of the key factors that explain the formation of the core shell systems. The other one will come from this slide here. And here I have this graph to the left that shows the relative stability of crystals of these metals, the bulk phases. So we know, it's well known, that most crystals are face-centered cubic structures. Some of them are hexagonal close-packed, and in this case, only iron is body-centered cubic. So we constructed, using this lab model that you see on the right side here, we constructed compact surfaces and measured the surface energy from this. So the surfaces were constructed from these most stable crystals, and the surface that we chose were the surfaces that we chose were the most stable surfaces, the most compact ones, because our nanoalloys, they are compact. There are variations, but they are mostly compact. So we measured the surface energy. And we came up with this model that predicts the results, the results that I showed previously. So the radii of the atoms, well, first of all, what you see here in blue is everything that has a lower value than platinum. And what you see in red are the numbers that are higher than the value for platinum. It's a simple way just to put into evidence. But we highlight here the radii, the surface energy, calculated in the way that I showed you right previously, and we also put the electronegativity. Why? Because we know that these atoms, they transfer charge to each other, and the charge transfer is an important factor to the stability also. So atoms that are smaller than platinum, they will be located in the core region. If we compare the pure icosahedron clusters, and we try to compare the average bond distances of these pure icosahedron with the nanoalloys, with stable and unstable nanoalloys, if I take one nanoalloys that has gold in the core region, I will see that this core is approximately 3%, the atoms are approximately 3% closer to each other. The average bond distance has this difference. They are more compressed. So if I try to put the larger atom on the core region, into the core, the surface will compress the core. And this generates strain. And this strain makes that the nanolloy is not as stable as it could be if the atom were on the surface, if the larger atoms were on the surface. Each composition has its own behavior that you can see in the pictures. And the surface energy is also a simple concept. The element, the metal that has the corresponding surface with the lowest surface energy will have a strong tendency to occupy the surface, because the surface energy can be thought of as an energy required to obtain a surface from the crystalline phase, okay? And the charges, this is just an expectation if you consider only the electronegativity. Of course, in fact, we have other effects, we have surface effects that also come into play to define this distribution of charges. And to close my talk, I would like to come back to the main results, and let's see if we can really try to understand them. I highlighted here 2 examples. All of them can be explained by these properties, but let's think about some of them just to simplify. Think about the 3D metals. In the most stable cases, the smaller atom, the smallest atom, in this case is the transition metal, it's always in the core region, the most stable configurations. If I try to put these atoms in the surface, the energies skyrocket. The energies are higher. And if I adjust the compositions, if I adjust the arrangements, I will see beautiful trends. I will see beautiful trends. If I have few platinum atoms, they are larger. They like the surface region. They want to, otherwise you would have strain. And I highlighted also the palladium case, platinum and palladium. If you come to the radii, you will see that they are very close to each other. The radii between them, it's almost the same value. So this case is driven more by the surface energy. There is a trend to locate which one? Palladium. Palladium will be located in the surface region, mostly. It's what you see here. Think about the zero in energy. Palladium is tending to be in the surface region. You can take any other example that you want, and you can think about them using these two simple properties that are easy to calculate and easy to understand. So thank you again for the opportunity. Thank you for the universities, every one of our colleagues, the center, our group, and the funding agencies. Thank you.